looking at lesson 8 in our lecture notes, which starts on page 17, and this is our last lecture on kinetics, and we want to focus just on this catalyst and intermediate species. In past lessons, I've referred to them in our mechanisms, and we want to delineate between them and show you how they look on a graph as well. So first, let's make sure we have the definition of a catalyst, which I've written in for you. It is a substance that increases the rate of a chemical reaction without itself being consumed. A heterogeneous catalyst is a reactant and catalyst in a different phase. And those pictures you have in your notes, hang on a second. Just a second. It's not a very good picture, however, in your textbook, that's right out of your textbook, I think it's on like page 607 or 609, and that is how catalytic converters in cars work. You've got a piece of metal that is serving as the catalyst, and these two gas molecules, in this instance, I think it's propane and hydrogen, or ethene and hydrogen with a double, the ethene has got a double bond. And what happens is they are absorbed by the metal. In other words, they're attracted and kind of stuck on that metal. And in the process of that attraction, the attraction actually breaks the bonds and separates the hydrogens. And then the hydrogens migrate over to the ethene and bond and add on to that double bond. And then once it's a more stable, the ethane then is not as attracted to that metal surface, and then it floats free. So it is kind of just working at bringing these two together, and as you can see, it is heterogeneous. It is a solid. The reacting molecules are gases, and it is not involved in the reaction at all. However, if we just had to rely on that hydrogen reacting with the ethene, it would be a very long process just on its own. So this catalyst speeds up the rate in which those hydrogens are added to the double bond of the ethene. Okay, a homogeneous catalyst is reactants and catalysts in the same phase. Hang on. Yeah. I'm videotaping. That's okay. You didn't.
I'm not doing DLC.
Oh, okay.
I'll talk to you.
Yeah. Sorry. I don't know how to pause this thing. If I stop it, I got to start over, so I apologize for that. Okay, homogeneous is just they're in the same state. Now, a great example of this is in your body. In your body, you have enzymes, all right? And we'll call this an enzyme, and it has a shape like this, all right? And there's a reason it has a shape like this. Let's say you have a protein or something that you've digested and your body has a hard time breaking down this food, protein, whatever, into something useful. And this protein just happens to be shaped like this, all right? Now, this protein, like that, your body has to break down to use. It can't use it like this, all right? So it has to decompose into something different. However, it takes your body forever to do this. So the function of this enzyme, this is so cool, is it attracts this particular molecule because it's a lock and key type shape. And then what happens, and this is shown on this diagram, is that when it locks in there, it then breaks that molecule into those shapes then that your body can use. And once it is broken, it is then released from that enzyme, and then another one goes in, so this enzyme remains intact, and its sole function is to quickly break down molecules that your body on its own could not break down quickly. If you were relying on it for nutrition, you might starve to death by the time it actually broke it down on its own. So a catalyst speeds it up. It is not involved in the reaction, and it can be in the same state or a different state. All right? And that was an example of biological applications that are now going to be showing up on the exam. All right. Let's go back to lesson 7 for an example, because on your homework in multiple choice, I think it's all multiple choice number 10, it said, how does an enzyme affect a net ionic equation of a reaction? And I didn't think that you could really delineate between answer C and D. They both said it'll have no effect on the net ionic equation. And if you'll look at the reaction of hydrogen peroxide with the iodide ion on the top page 16 of your lecture notes, you see that it is actually a reactant and then an eventual product, correct? However, it cancels out, so it would not be in the net ionic equation. But it is not in the net ionic equation. I think your homework says it's the same because it's neither reactant or product, and that's not true. We can see it is a reactant and then an eventual product. It just cancels out. So the net ionic equation doesn't show it, but it did react and form an intermediate species and then get spit out. Now, the example of the catalytic converter, there would be one that it is not in the net ionic equation because it is neither a reactant nor a product. No, it just was a facilitator, to get those gases to where they should be. So I think on question 10 of your multiple choice homework that you could make an argument for either C or D. All right? Okay. All right, so the function of a catalyst, what is meant by heterogeneous or homogeneous, some biological application of a catalyst, also how it shows up or doesn't show up in an equation, depending on the type of catalyst it is. Now, another thing that your free response, and this is usually worth, I've told you this in previous lesson, a point, graph the difference. All right, now there's 3 different graphs, that I can think of. They all always come up with something you hadn't thought of, but let's look at a kinetics graph, all right? All right, now a kinetics graph might be graphing concentration versus time or something like that. And, all right, and convention is, and you would write this as a key, the solid line is uncatalyzed, and a dotted line is catalyzed. And they would say on this graph, show how the graph would be different if we had a catalyst. Well, what would happen is that in comparison to this, it would have a steeper slope. All right, so it would take less time. Less time when this is y over x would be if x had a smaller value. All right, so that is how the catalyst, uncatalyzed and catalyzed on a kinetics. Now, what if you were looking at an equilibrium graph? All right, and this is the course of the reaction. And this is concentration of reactants versus concentration of products. Here's just a typical equilibrium graph. Now, how would this change if we added a catalyst? Well, we would just get to equilibrium more quickly. So you would show that. See, we get to the same equilibrium, but we just get there more quickly. So this is a steeper, all right? It's steeper and saying, I get to equilibrium more quickly than I did without the catalyst. All right, so let's get a graph of catalyst and uncatalyzed. And finally, in an energy profile, and I showed you this, I think, in lesson 1, okay, if we were looking at the energy change as we went to a course of a reaction, and we had reactants and products, all right, the solid line representing the uncatalyzed, what this would look like if it was catalyzed then, would be the dotted line would be there. And what that is doing is lowering the activation energy. Okay? So it doesn't take us as long to overcome that initial nudge to get this going. All right? So here's 3 different ways you can be asked to graph. And if you are asked a different way, then just use this principle. All right? Apply this principle of what will demonstrate that it's quicker or lower energy. All right? And in a graph, it is a steeper slope. In this, it's lower activation energy. Okay. Now, they also want you to be able to identify a catalyst and an intermediate species given a mechanism. All right, so there's this mechanism, and they'll say, okay, which of the following, and it might be more than one. Right? So from this mechanism, which is that mechanism of hydrogen peroxide being catalyzed by the iodide ion, all right, we said that a catalyst is that it reacts and then it is spit out. Right? So we first see it as a reactant, and then we see it finally as a product. So I look at that mechanism and I say, what shows up as a reactant and then is spit out at the end as a product? And this is the only one in that reaction that fits those parameters. So the iodide ion in that mechanism is acting as the catalyst. All right, now, an intermediate species, and I'm just going to abbreviate that IS, is formed and then consumed. So the first place an intermediate species is going to show up is as a product, and then it's going to show up as a reactant. All right, because we got to form it. Where do you form something? On the product side. So now I look at my mechanism, and remember, if they show you a 4-step mechanism, there could actually be several intermediate species. All right, so don't just pick one and move on. Make sure you really analyze this. So I look at this mechanism and I say, what shows up as a product and then again as a reactant? And that is this particular species. Notice it's as a product in the slow step, and then it is a reactant in the fast step. It is formed and then it's consumed. So it goes away as well. All right? Okay, so this is the difference. And that's good on the multiple choice. They'll show you a mechanism and they'll say which of the following species is acting as a catalyst. Which of the following, is acting as an intermediate species. Being able to identify both, knowing this. Catalyst, reactant first, intermediate species has to be formed, product first. Okay, so now let's look at putting together everything we've learned in kinetics as far as relating it to an energy profile and understanding from an energy profile how we can interpret a mechanism if it's a detailed energy profile. On the last page of your unit, page 18, we start with two graphs that I've included for you. Now, I've left space on the right side because we're going to include a third graph, so don't get too carried away with your writing. All right, make sure you leave room for this, or you can write it on the back side too, so whatever you want to do. All right, one of these is an endothermic reaction and one of these is exothermic. Now, first of all, from thermo, do you know how to identify which is which? Okay, well, the top one is going to be endothermic, isn't it? Because we started, our reactants are at low energy, we had to input, and we got our products at a higher energy. The bottom one is exothermic. Our reactants started high, it released energy, and our products were lower. All right, now, let's be able to identify points on this graph. All right, the net energy right here is the delta H. The delta H is the enthalpy of the reaction. This is a state function, and it doesn't matter what we do getting from reactants to product, this is the end result. If it's endothermic, this is how much energy needs to be inputted to get these reactants to go to products. All right? This here is the activation energy. All right? The activation energy is saying, what is the nudge I need to give this reaction to get it to that transition state where it goes in, eventually goes into product? What is the energy hump, the energy obstacle that is holding me back? All right? And we call that the activation energy. Okay? At the top of this, first of all, a general energy profile always just looks as if it's a one-step mechanism. All right? Okay, so if this were, because energy profiles are just in a general sense, you know, if it was more specific to show the mechanism, it would look a little different. All right? So either this is a one-step mechanism, or they're just being lazy and saying, here's just a vague idea of what goes on with this reaction. All right? At the top of this activation is what we call, and I'll put a star there, the transition state. Okay? And what is a transition state? Right? A transition state could be, they also refer to this as an activated complex. All right, those two terms are used synonymously. All right, let's look at that reaction. Of ethene plus hydrogen going to ethane. Okay? That's what's shown on your drawing on that first page, 17, up at the top. Right? Okay, this is the reaction. We want to add the hydrogen onto that double bond. Okay, well, a transition state for this could look like this. Here's a momentary molecule that's reflecting as this hydrogen collides with this ethene. This bond here is breaking. Okay? We also have this bond loosening up. And we also have these bonds thinking about forming with this carbon. All right? So this is this nudge. We need to get this activation energy says, I need to get this to collide with sufficient energy and with the right orientation that we can get it to this point where it's saying, what am I going to do from here? What am I going to do? And then finally, what's going to happen is that this bond will break, this bond will break, and we will form this, and this is our product. All right? So we've gone from that transition state into an actual product. Okay? Now, an interesting thing is if we run the reaction in the reverse direction, this right here has a special name, and it is the reverse activation energy, all right? Because if we run this from product into reactant, then the energy obstacle we have to overcome is from this direction, isn't it? All right? So, and it is shown with like a little prime sign, okay? Or they might, well, no, that would be incorrect. All right, so the things on an energy profile is first to determine if it's endothermic or exothermic, relating where reactants and products are, where delta H is, and how that differs from the activation energy. Right, at the top of the hill is the transition state. All right, there's a classic energy profile. Now, an interesting note just to tie this back in with thermo. Remember that we said that the delta H of a reaction that goes this way, what is the delta H if it goes back this way? Right? It's the same value but opposite sign, right? If we said A goes to B, has a delta H of X, then B going to A has a delta H of negative X. One way it's endothermic, the other way it's exothermic, but the same value. Well, let's tie that in with this activation energy, all right? Let's say that it takes 4 kilojoules of energy is the activation energy. All right? And then the energy released as we go from transition to product is a negative 2 kilojoules. All right? Well, the delta H then for this would be 4 minus 2, or 2 kilojoules, right? Okay, because delta H is going to be the difference between the reactants and the products. All right, well now let's run it in reverse. Okay? In reverse, the delta H will be 2 minus 4 equals negative 2. Because now this is, I've got to input 2 kilojoules, don't I? And once that transition state is formed, it's going to release 4 kilojoules. So now it's going to be 2 minus 4, the same value, the opposite sign, all right? So that is how mathematically that the delta H for the forward and reverse are going to be numerically the same, but the sign will be different. If it's endothermic one way, it's going to be exothermic the other. And that's how you can see that, all right, by looking at those activation energies. Okay, now, what if you had a multi-step mechanism? Let's say I had a 2-step mechanism. All right, and let's go back to one that was easy from let's go back to letter C on page 15 in the middle, where we had, here was the reaction, A plus 2B goes to P. And we said a 2-step mechanism for this could be A plus B equals C, and then C plus B goes to P. All right? So we have C as our intermediate species. All right, so how would we graph this? Well, and let's just say for the sake of argument that this was endothermic. All right. That is how you would graph a two-step mechanism. All right? We would have this transition state. This transition where these two are breaking bonds, forming bonds, and in the meantime, it would be, let's go back to our ethene. Remember this? Okay, this was our transition state, all right? But let's say instead of going immediately into product, this forms something like, all right? Let's say it forms two intermediate species. Okay, it could have gone either way. We have this transition state, and in our first example, we just broke this, formed this, and it went right to product. But let's say instead, those bonds actually broke apart in a weird way and created these intermediate species. And then these intermediate species are going to go ahead and react to form the eventual product. All right? So what we do is the hill is the transition state, the valley is the intermediate species. That intermediate species then has to get with the reactants and form another transition state, and then we eventually have products. Okay, so in a one-step mechanism, we have a transition state and no intermediate. In a two-step mechanism, we have two transition states and one intermediate. Well, what if it was a three-step mechanism? Well, you got it. For a three-step, we would have two intermediate species and three transition states. Okay? So our transition states match the number of steps, and our intermediate species are just one behind that. Okay? So one step, no intermediate species. Two steps, one intermediate species. Three steps, two intermediate species, and so it goes on. All right? So an energy profile for a multi-step mechanism. Now you can see, going back to other energy profiles, why they just usually just write a general one, and they don't take it into account the steps of a mechanism. All right, so I've shown you, our last thing of this notes is saying, how does the catalyst and intermediate species fit into this? Well, I've shown you how the intermediate species and the transition states are interpreted on an energy profile. All right. How does the catalyst? Well, we've alluded to this. We said what happens with the catalyst is that it lowers the activation energy, right? So instead of having an activation energy this big, we have an activation energy that is only this big. We have a lower threshold that we have to get over. All right? So this is how it's catalyzed. If this were a multi-step, so let's draw this really weird looking. Sorry. Okay? Let's say this is your reaction. It's two steps that forms one intermediate species. Well, we might do this. The catalyst, all right, would just lower the activation energy. Still be two steps, still have an intermediate species, but it would not, it would be a different route. It would form a different intermediate species, all right? So a catalyst provides a different pathway. However, the end result is that it has no effect on the delta H. Right? Delta H is a state function. State functions say final minus initial, doesn't matter the path we take to get there. Right? It will affect the activation energy. It will lower the activation energy. It will have no effect whatsoever on the delta H. That is independent of a catalyst. All right? A catalyst will affect the kinetics, though. All right, so that is it. That is our unit on kinetics. You should be able to do all your homework